Hello Year 12 Extension 1. In this video I'm going to develop the connection between the expansion of a binomial and Pascal's triangle. You may be familiar with Pascal's triangle as it appears down here, in that it's just a triangle with a sequence of numbers. There's a quite common and easily recognisable pattern here to Pascal's triangle, in that it begins with a 1, then the next row begins and ends with a 1. Each row begins and ends with a 1, and we get the other numbers within a row by adding the previous digits above it, the digits above it from the previous row. So you can see this 2 comes from adding 1 and 1. This 3 comes from adding the 2 and the 1. This 6 comes from adding the 3 and the 3. And 10 comes from adding 6 and 4. If you haven't looked at Pascal's triangle very much before, then you might spend a bit more time on it and become really familiar with it, because it forms a lot of the basic understanding in an expansion of a binomial. Okay, so let's have a look now at the expansions of the binomials. So we're going to expand a very simple binomial, 1 plus x, to the n, where n will start with the 0, and then we'll put n is equal to 1, 2, 3, 4, etc. And realise that back when we did polynomials, that when we expand out a binomial, then we get a polynomial in x, and you'll see if that there's a connection between the number of terms and the power of the binomial, in that you get one more term than the actual power. So if you're raising something you're squaring it, you all are very familiar with, you get 3 terms. Square the first twice, the product of the 2, square the last. So the power was a 2, but you get 3 terms. Power is a 3, you'll get 4 terms. I guess there's only one exception to this, in that when you expand a binomial to a power, you get a polynomial, in that when we look at the very first one, it's a rather unique polynomial. I guess it's the constant polynomial, in that the result is just a constant. Okay, let's have a look. So when you've got 1 plus x to the naught, anything raised to the 0 power is a 1. And there's nothing more to that one. 1 plus x to the 1, anything raised to the power 1 is just itself, so you get 1 plus x. I'll just try to make this a little bit more obvious. It's 1 plus 1x. And there's nothing more to that. Just keep reinforcing these properties, which become so important later. It's that when the power was a 1, we have 2 terms, and the numbers are 1 and 1. Okay, let's move on to expanding a binomial raised to a power 2. You know the pattern here. Square the first, twice the product of the 2, square the last. And again, I'm just going to add this coefficient in, and probably already you're seeing we've got, if I just single out the coefficients, a 1, a 1, and a 1, a 1, a 2, and a 1. On a cubic, no, you'll just have to take my word for it. I'm not going to spend the time on expanding that, but it expands to 1 plus 3x squared plus x cubed. So you can see 4 terms power 3, but 4 terms. Coefficients now being 1, a 3, a 3, and a 1. You can see we're building Pascal's triangle here. And the connection becomes pretty obvious that the coefficients of the terms in the polynomial reflect the numbers in Pascal's triangle. So raising 1 plus x to the 4th, and again you'll just have to take my word for it, you get this expansion, and I'll put the coefficient in. So we're getting a 1, a 4, a 6, a 4, and a 1. And again, this is Pascal's, the 5th line of Pascal's triangle. 1 plus x to the 5 gives a 1, a 5, a 10, 10, 5, and a 1 as the coefficient. And you can see that would give 1 and 5 and 10 and 10 and 5 and 1, being the numbers in the 6th row of Pascal's triangle. So you can see there's a very clear connection between Pascal's triangle and an expansion of a binomial. And just to summarise a few key points, you'll see that, hopefully you see that the term with the highest power of x in 1 plus x to the n is x to the n. So the highest x term, the term with the highest power in 1 plus x squared is x squared. When we raise a binomial to a cubic, the highest power of the x is a 3. There are n plus 1 terms in the expansion of 1 plus x to the n. You've heard me emphasising that. It's 1 more than n in terms of the number of terms. The coefficients are shown by an appropriate line of Pascal's triangle. Each coefficient is the sum of the two numbers from the line above. The coefficients are symmetrical. So oops, I don't know how that happened. A 1 and a 1, 5 and a 5, a 10 and a 10. On the other hand, we've got a 1 and a 1, a 4 and a 4 and a 6. The first and the lowest coefficient is always 1, and the second and the second last coefficients are always the same as the power. Now, we're going to have a look much later at some proofs of some of these, mostly because they contain some very important techniques that you'll use in questions a little bit later in the chapter.